Anybody know? Has anybody heard that term before? In what context have you heard that term?
It depends, like if you're something that hasn't undergone chemical. I don't know about chemistry.
Organic materials? What are organic materials? Maybe we can define it against something else. What would be inorganic? What would be the difference between organic and inorganic? The inorganic is not organic.
Something that's man-made, something that's created.
Perhaps synthetic. Yeah, it's actually kind of a nonsense word in that it meant something at one time that it no longer really means. A long time ago, we thought that there were two completely distinct groups of compounds. There were the minerals, the inorganic things, so rocks, that sort of stuff. And then there were organic things, which came from living things. Because we used to think that there was no way that these could be the same. That you could never make, that a molecule, we knew about molecules and about materials, but we thought that molecules or materials that you got from a living thing, like a person or a plant or whatever, could never have any cross or be the same as something that we got from a rock or a mineral or something that was never living. So there was a sort of like life force that was in living things that is different from non-living things. So chemicals were separated into these categories of inorganic and organic. And now we know that's not really the case. In fact, it was shown initially that a compound that came from a rock could be chemically broken down and turned into an organic molecule. And we know we can kind of go back and forth with that now. So to have this rigid distinction no longer really makes sense because we know that molecules are molecules and atoms are atoms, and it doesn't really matter if they came from a living thing or a non-living thing. But we still use this term organic chemistry. We just define it a little bit more specifically in terms of the chemistry. And we say that this is the chemistry of compounds made mostly from carbon and hydrogen. And then they have lots of other stuff also, nitrogen, oxygen. They can have all kinds of other elements in them, but they're primarily carbon and hydrogen. And so we say that the compounds or molecules made mostly from carbon and hydrogen are organic molecules. And the chemistry of studying those things, or the chemistry or study of those things, is organic chemistry. So that's what we're talking about in the chemistry context when we say organic, is compounds made mostly from carbon and hydrogen. All right, let's look at what that means in terms of what these things would look like. So we have a carbon atom. How many valence electrons does a carbon atom have? Four? Four, yeah. All right, there's our Lewis dot structure of a carbon. Bonds does carbon want to make? 4. Why? Right, because we need 8 total, or 4 pairs of 2. So to get 8 total, that means we need 4 more electrons. So we're going to react this with 4 other spots, right? 4 other electrons that can come in and share, and that's going to give our compound. So our simplest organic compound is going to be a carbon atom plus 4 hydrogen atoms with its 1 electron. And we can draw this structure that we call methane. This is the major component of natural gas, like we get out of our gas taps here that you burn in your Bunsen burner, or the gas you burn in your house to keep warm one of these lovely cold days and nights. So This is not really a chemical reaction. We don't have free carbon atoms combining with free hydrogen atoms, but that's the basic idea, is that these things would come together and make methane. And we draw that, but that's actually not a great picture of what a methane molecule might look like. And the reason is because the geometry is off. We didn't really get into the geometry of molecules, but it turns out that a methane molecule looks more like this. I'm going to just pull this picture in because then we'll draw it later. Looks more like this, with the carbon in the middle and the hydrogens around the outside. So it's kind of a three-dimensional structure. It's a little bit hard to draw on paper. Why do you think it adopts that structure rather than this? I'll give you a hint. It has something to do with this angle. Why is that a better structure for methane than the flat version? How close they are, right? What were you going to say?
Something to do with polarizing?
Not polarizing, because carbon and hydrogen are essentially nonpolar.
But the way it's going to connect with other structures?
That will affect how it connects with other structures, but it's really just, what did you say again? How close they are. That when you have a structure like this, what is this angle? Yeah, that should be a 90-degree angle if it's drawn, if we draw it like a perfect T like that. And if it adopts this kind of a configuration, this becomes a 109-degree angle, so a wider angle. So those hydrogens can be further apart from each other in this type of a structure. In here, they're actually closer together. The outsides of atoms are the electron clouds, and electrons are negatively charged, and we know that two negative things will repel each other. So they want to be as far apart from each other as possible. And that's why it adopts this kind of an arrangement, which is known as a tetrahedron or a tetrahedral geometry. If you draw lines between the hydrogen atoms, yeah, and you imagine another line going back, that's a shape called a tetrahedron, which is a shape with 4 equal sides, 4 equal angles, and 4 equal edges. And so the carbon atom would be in the middle, and the hydrogen atom would be at each point. It's kind of like a pyramid, but with a triangular base instead of a square base. So we'll keep in mind that's the geometry when we talk about organic compounds. That's the shape of the bonds in the organic compounds. All right.
All of them?
Well, no. But the ones that we look at first anyway. So we're going to look at some different categories of compounds. We're going to talk about how to draw them, how to name them, and some of the chemistry involved in them. So we'll start with the simplest ones, which are the alkanes. Alkanes are the simplest because they are only carbon and hydrogen, no other atoms. With only single bonds. So carbon and hydrogen connected by single bonds, those compounds are called alkanes. Now alkanes don't do a whole lot. They burn, and that's about it. So we don't really talk a lot about the chemical reactions of alkanes, but alkanes are really important because of how they burn in terms of the very light alkanes are things like natural gas. Slightly heavier ones are liquid fuels like gasoline. And then the heaviest and longest ones are things like waxes and oils, which also burn. All right, so let's look at some of these. The smallest one, we'll just make a little table here. We already talked about CH4. And we'll keep drawing the structure kind of in the squared off way, just because it's easy to look at. But we always want to keep in the back of our head that that's not actually the structure, that really it's this kind of three-dimensional zigzag structure. And we'll get into that more in a little bit. So that's called methane. And then the next one is going to have 2 carbons. And then how many hydrogens do we need if we have those 2 carbons? 8, 6, 4 each, 6. Why 6? How'd you come up with 6?
Because one of them is already shared.
Oh, shit.
Yeah, because we need 4 bonds to each carbon. So that means that each of these needs 3 more. 1, 2, 3. So the molecular formula for that one is C2H6. And that's okay. See if you can draw the next one in the series. 3 carbons, and then tell me how many hydrogens you need for that. What do you think? C3H8? Sounds good. So we've got 3 carbons in a row. And you may notice, not such a big deal, but it's starting to become a little bit tedious to draw all these hydrogens. You notice that? So imagine when we get to like 8 or 10 carbons, it's going to be kind of a pain in the ass, right? So we'll think of some ways to, next thing we're going to talk about is some ways to abbreviate this a little bit. Anybody know what this would be named? Yeah, right. We'll just keep dropping letters until we have nothing. No, this one actually has a different name. This is called propane. Propane is also light. It's also a gas at room temperature and standard pressure. It's what we use to power like a gas grill or a torch or a lantern. Comes in cans. If you live off in the country somewhere, you might have a huge propane tank out in your yard to run your house off of. And so this one's C3H8 propane. All right, so now let's talk about what we call a condensed structure, or a way to condense this drawing down that still gives us the same amount of information, but in a way that's a little easier and quicker to write. So a condensed structure for propane might look like this. All right. So what we've done is we've collapsed the hydrogens down onto each carbon with a little subscript number telling us how many hydrogens are supposed to be on that carbon that comes right before it. So this carbon has 3 hydrogens attached to it. This has 2, and this has 3. So there's the 3, there's the 2, and there's the 3. This gives us a little bit more information than just this formula, because it allows us to really visualize how this thing is set up. It's 3 carbons in a row with the appropriate hydrogens in the appropriate places. A formula like this makes us do a little bit more work to actually figure out what this thing looks like. So with organic structures, we often prefer to write formulas like this, which is called a condensed formula, rather than something like this, especially when we start getting up in numbers. These molecular formulas are really only useful for telling you the number of each type of atom. So it's got this many carbons, this many hydrogens, but for more complex structures is to keep those hydrogens collapsed, but still actually draw the bonds in like that. So you can imagine if there's a bunch of branching stuff as this gets bigger, that might be a nice way to write this.
How can you differentiate though between, like, if you're adding 2 things together? together, if you're reacting two things together, that as a molecule or just as an individual substance compared to, you know, like a polyatomic ion, I think there's actually two different things combined. We're separating them and now we're doing it.
Right. I think the key is to look for the carbon and the hydrogen. So again, if you don't see things like metals, then
If it's just
it may not be.
hydrogen, you know, it's an annotated.
Yeah, and I would say that's not always true, but for what we'll experience, that's a good rule.
So you want us to know all three ways to do it?
Yes. All right, so now I'm just gonna tell you that the next one is called butane. It has 4 carbons and some hydrogens. Butane is, now we're getting to the point where you can lighter fluid is predominantly butane. It is a liquid, but it vaporizes very, very quickly. So see if you can come up with the number of hydrogens and draw each type of structure. The full Lewis structure with all the bonds and atoms, and then the condensed structure over on the right. All right, got it? How many hydrogens? 10. That's going to look something like this. Have you noticed any sort of a pattern in the number of hydrogens? They're in even numbers. Anything else? If I told you how many, or if I asked you how many hydrogens would be in a compound with 20 what? Why 22? Yeah, if you think about how these things are, for each carbon, there are going to be 2 number of hydrogens as carbons in these types of compounds. So it doesn't matter how many carbons you have, you can always find the number of hydrogens by just doubling it and then adding the 2 for the ends. All right, so this is butane, and then our condensed formula would look something like this. Good so far? Okay. So for the next group, we're not going to go through the whole thing here. Let's paste a little table in. This is from the book. So this tells you how to name the different members of this class up through 10. And I believe on the objectives for this chapter, it goes up to 6. So those are the names that you should know. Any more than that, I'll give you those. So methane, ethane, propane, butane, pentane, and hexane. Once you hit 5, they go up by familiar prefixes. Pent always means 5, hex means 6, hept means 7. You may have seen those prefixes before, but the first 4 kind of have their own weird names just because of where they come from. I'm not sure which page this is on. It's going to depend on which edition of the book you have, but you'll see it in there. It's actually a larger table than this. It has all the structures written out also. Through 6, yeah. And so something interesting is maybe a strong word. Something happens when you get up to that actually to the fourth member, where you can start writing these things in slightly different ways. So if we go back to this structure of butane here, if we think about the molecular formula C4H10, that fits here, but there's actually another way to make a C4H10 that is a different structure. And that would be if we took 3 carbons like this, and instead of putting that fourth one on the end, we put the fourth one coming off the middle carbon here. And now we still need to add our hydrogens, so we fill up our carbon to make sure they all have 4 bonds. Like that. And this is actually a different structure. This is not the same as that previous molecule that we wrote. And it's also not called butane anymore. We'll talk about how to name all kinds of different compounds if we get to it today.
Yes, but if it has similar hydrogens and carbon, how is it not the same?
Right, how is it not the same? Well, if it has the same numbers of hydrogens and carbons, the reason that it's not the same is that it's not connected in the same way. So we might say here we have a carbon with 3 hydrogens, one with 2, and then one with 3 all in a row. And here we have a carbon with 3, a carbon with just 1, a carbon with 3, and then there's another carbon with 3 coming off of that middle carbon. So this is a different compound, and in fact, it behaves differently. It has different boiling points. Sometimes these have different colors or different ways that they behave and reactions, depending on that. And we actually have a special name for these types of compounds. These are called isomers. Isomers are molecules with the same formula, so same number of carbon and hydrogen, but different what we call connectivity. So those carbons and hydrogens are connected in a different way, and in a way that can't be made the same just by rotating or twisting things around. Single bonds between carbons can rotate and twist. So something like this, that's actually the same as this, because that's just kind of a twist of a bond. This is fundamentally different because you had to actually break something off the end and stick it on somewhere else to make something new, to make a different thing.
What is it called though? If it's not butane, what is it?
In this case, it's called 2-methylpropane. We'll get to that, to the naming rules in a little bit.
But if everything is dictated by how many protons and,
Mm-hmm.
I mean, if it's dictated that it's gonna be the same, it's C4H10, how can it be something different?
Well, so that's a new thing now that we haven't really seen before, that it's not just about what atoms are there, it's also about how they are connected to one another.
How would we differentiate them if we were to see it? Like, how would, because we're not
Right.
as familiar with.
Right. So that's why something like this is not as useful of a designation. Because if you say C4H10, you could actually mean this or this. What?
What is the name of the bond?
This is called 2-methylpropane. We'll get into the names in a bit. But that's why we don't use these types of formulas as much with organic compounds, because we have to have a designation that says this is one thing and this is another thing. So instead, we might use a condensed formula. A condensed formula for this one would look something like this. So that would be a clear way of saying here, look, this is different from this. We're talking about two different molecules here. And you're right that we haven't seen that before. If we talk about sodium chloride as NaCl, there's nothing else that's NaCl, so there's never a reason to actually show a structure. But when we say C4H10, we could be talking about two potentially different things.
So is that why we're learning, is that why we're memorizing those top six?
Mhm.
Because those are the ones that we need to identify as those, and then anything else we should assume it's an isomer? Or-
Yeah, and we're actually going to learn how to name all these isomers as well, because there are some rules for doing so. But before we do that, we have to get some more isomers. So let's try to do this together. Let's look at the next class of them, which is C5H12. So these are pentane. There are three isomers of pentane. There are three isomers of C5H12. I'll give you one of them. So there are three different molecules that are connected in different ways that are still C5H12. So see if you can find one or two of the others besides this one. And if you think you've got one, come up and put it on the board over here, and we'll take a look at them and see. Let's see if, as a class, if we can come up with the other two potential isomers. As a hint, I think it can be helpful to look at this just with the carbons and leave the hydrogens out for now, and then put the hydrogens in later. See what you can come up with. Have we got one yet? You think? If you think you got one, put it up on the board. Let's see. Doesn't have to be right. You can just come up and draw a turkey or something. Try something.
There's three of them, is that right?
There are three total, including this one, yes.
So I got one too.
Okay, let's see what you get. Go ahead.
And what is this called? What is this one called?
Pentane is that.
Pentane is this, but what is it?
The other ones will have different names, yeah. So what do you think about this one that's already up there? Is that, everybody, would you say that's different? Does that fulfill both criteria? Same formula, different connectivity? Okay.
There's 12 hydrogens on it.
Okay, what do you think about this one?
That's the same as the one.
You think that's the same as this one?
No, there's one carbon here. There's now separated.
Okay.
And
All right, but you're saying this is
Same as the one.
same as the one up on the board or up on the screen? Why? How would you know?
Because it just told us it was just bent differently, but still, you're not taking another carbon and putting it in between.
Okay.
I didn't know.
What do you think?
I just, yeah, because, no. Yeah, three. No, because there's, yeah, there is 2 of 2. You think so?
Well, let me
I
see.
wasn't really paying attention. I just.
That's fine. Yep. Anybody? Let's see others. Anybody got any other ones? Go ahead, Alex. So I'm gonna put this one up on the board here. I'm gonna draw these without the carbons on them for now, but all right. Then you've got this one here. What do you think about that one?
That was different. Yeah.
That looks different. Yeah. All right. So let's look at this one then. One way that you can determine, because really the hardest part of this is figuring out whether ones that you've drawn are actually the same as other ones or not, or if they're actually something new. So one of the ways to do that is by numbering the carbons in a row of a chain. Just numbering them from 1 to whatever, in any way, and trying to find the longest possible chain that you can in the molecule. This will become important when we talk about naming later also. But like for this one, I could say, all right, here are 5 carbons in a row that I can number 1 through 5, either left to right or right to left. In this version down here, the most I can get in a single chain is 4. And then I have to stop and look at another one that's connected in another way. You see that? Over on this one, what's the largest number in a row? 3, and you can go any way you want. Just to try something different, we'll do this one. But there are 3 connected in a row no matter where you start and where you end in this case. You can't get more than 3. So what about this middle one? How many are connected in a row? 5. If we try to get our longest chain, we can get 5 in a row with nothing else connected around anywhere. And that tells us that this one must be the same as this. And in fact, if I don't know if I can do this on my thing, but if I can like pull this around here, does this rotate? No, I can't rotate in this one. But if you can imagine that sort of twisting around, you get the idea that we could twist that around and kind of stretch it up here and take this one and stretch it up here, and we'd have the same thing again, 5 in a row. Yeah. So these are the same.
So I just moved it, so that one's different,
Mm-hmm.
and that's all you need, or you need one?
That's it. That's all of them.
So I just did one where under number 3,
Mhm.
the other carbon was under number 3 instead of under number 2, but that would be the same as what you have here.
That's right. So if we did, let's look at that one. Like that.
Yeah.
So this is the same as this. If you imagine this thing flipping over, you've got the same thing as you've got here. Yep. All right. Let's see. Oh, I didn't save this. Let's save this. Okay, now let's talk a little bit about naming these things. And then we'll get into some larger ones. Much like with our other compounds, we want a systematic way of naming these things. We want a set of rules that if we follow those rules, we will always get the same name. Anybody in the world following the same rules will always get the same name. I mean, assuming that you do it right. But before this convention, all these compounds had different random names, mostly depending on where they came from, what sort of a thing they were extracted from, what country they were from, whatever. So if you learned organic chemistry, you just had to learn hundreds and hundreds of different names of different compounds so that you knew what you were talking about. And at some point they said, well, this is kind of ridiculous. There should be a standard rule that everybody used to name these compounds so that when I say 2-methylpropane, to anyone else who knows the rules, they know what that means and they know we're talking about the same structure. Kind of like when we say iron 3 chloride, that only refers to one type of formula and not other things. So here are our rules. Let's take a compound like one of these that we just drew as an example. Let's take this one. So the first thing that we're going to do is we're going to find the longest continuous carbon chain. So the longest chain of carbon atoms in a row without breaking into something else. For this example, we have two choices. Do you see the two choices? They're each the same length. We can go with this one, 1, 2, 3, 4, or we can go with this one, 1, 2, 3, 4. Everybody see those two? This one or this one? All right. So for now, let's stick with this one. That's going to create our base name, what we say kind of the main part of the name. We're going to take whatever that is and go back to our chart and figure out how many carbons are in that chain. So how many carbons are in that chain? 4. We go back to our chart, and we know that 4 carbons are called butane. So this name is going to end with butane. Good so far? Then we're going to number the carbons. Wait, not yet. Hold on. Next, we're going to find what we call the substituents. That's a fancy word for things hanging off of the main chain. It means substituted for hydrogen. So things other than hydrogen that are connected to the carbons on that main chain. In this case, what is a substituent? The what?
Another carbon.
Yeah, another carbon, the CH3 here. So we'll circle that. There's a substituent. So here's our longest continuous carbon chain. There's our substituent.
So either way, we have on the other way, and still the CH3,
Right. All right. So now we're going to number the carbons on the main chain so that substituents are closest to 1. So we're going to just number them 1 through 4, since it's a 4-carbon chain, so that the substituents are closest to 1. What that means is that we have 2 choices to number the main chain. We can number from left to right or from right to left. So what's the better choice based on rule number 3? Left to right. So we go 1, 2, 3, 4. And so we're going to add as a prefix our substituent. We're going to use the same language or the same types of language that we use up here, but rather than end in ane, to show that this is a substituent, we're going to end in YL. So that substituent is called methyl. Meth because it's 1 carbon, and YL because it's hanging off of the main chain. So methane would be CH4. That would be a molecule by itself. Methyl is a 1-carbon CH3 group that's hanging off of another larger chain. Just a little bit lower so you can see it. And then we're not quite done yet because we have to specify where that methyl group is. And we see in this example, it's coming off of carbon number 2. You see that? So this becomes 2-methyl butane. And that is the full name of this molecule. That is an unambiguous name, which means that there can be nothing else called 2-methyl butane except that particular structure. So when we say that name, we are always and only referring to this particular molecule.
Will you say that last, what would be number 4 again, about the methyl? Methyl?
We write this down here, maybe. So let's see. Substituents get a YL suffix or end part. And get attached to the main chain name with the numbers. Does that make sense? So the substituent gets that YL suffix, and you stick it on that main chain name with numbers telling you where that is on the chain.
So the meth we got because it's on the second.
No, the meth we got because it's a 1-carbon substituent. So let's look at some different.
Look at your little chart.
Let's look at some different substituents and what they would be called. If it's a CH3 coming off something, that's called methyl. If it's 2 carbons coming off of something, so here's some sort of a main chain up here. If it's 2 carbons coming off something, that would be called ethyl. If it's 3 carbons coming off something, what do you think that would be called? Close. Yeah. Propyl. So not propane, but propyl. Propane would be just the three as the main part. If it's coming off of something else, it becomes propyl. All right, let's practice this a little. So let's look at one of our other isomers. Leave all these rules up here for now.
What was it originally called? Originally it was pentane, right?
Well, the straight chain, so if we go back up to our isomers here, if we were using these rules to name this molecule right here, we would say the biggest chain is how many? 5, and no substituents at all. So that's just pentane. This molecule is 2-methylbutane, but it is an isomer of pentane because it's still C5H12. So this molecule and pentane are isomers of each other, meaning they have the same formula, but they're connected in different ways.
Would it be the same if you said 2 methyl? Or if you put the methyl last and then butane first?
No, you got to do it like this.
How do you then, like if you were to give us this,
Mm-hmm.
how would we track that back to pentane, since pentane's not even in the name? We would just know that.
Just from counting up the carbons.
Carbons.
You have to count up and see that there are 5 carbons.
Originally, it starts out with 5 carbons, so it's got to be.
Yeah, so the formula, the molecular formula of this molecule is C5H12. Right, if you count up all the carbons and the hydrogens, you get C5H12. All right, let's try another one. Let's look at this other isomer. And talk about how to name it. So this is the third one up here in green. What's the longest chain? Let's go back to our rules here. So first, longest continuous carbon chain is how many? 3. Where do you want to put it? Does it matter? No, it doesn't really matter in this case. So let's just put it around here because that's easier. Actually, let's do a different one just for fun, just so we see how it might go a different way. Because that could also be a longest chain, right? That means that these other parts then are called what? Right, these are the substituents. And in this case, there's 2 of them now, because there are 2 groups that are not part of that main chain. When we number our main chain then, does it matter if we go from where we start? Does it matter where we start?
No.
It doesn't in this case, because it's symmetric. So we'll go 1, 2, 3. So what is our base name of this chain then? Propane. We got 3 carbons, so this is going to end in propane. And this time, it's going to be a little bit different because we have 2 substituents instead of just 1. So we can't say just, it is still methyl because those 2 are separate, they're not together. So it's still methyl, but there's 2 of them. So we say that this is dimethyl, di meaning 2. Just like the naming the covalent compounds like carbon disulfide or something like that. So we've got 2 of them, so dimethyl, and we have to actually number each one. So these methyl groups are on carbon number 2. Everybody see that? So that makes, and the other one's on carbon number 2 also. So the way we write that is 2, 2 dimethyl propane. You see how each part of that name, where those come from?
So the main chain is always going to end in A and N.
For these compounds, yeah. All right, let's look at a couple more. I can get my examples here. A little bigger, a little trickier. Same procedure. So follow those rules. See if you can come up with a name for this one. And then we'll look at it together.
Is the bottom one supposed to have a connecting?
It could, yeah, that would be another way to write it. Yeah. So those two are connected to each other. And you could have totally crazy names here. Just try to get something and see if you get
Can
stuck.
we see the list again of the
Yeah.
hydrocarbons?
Oh, this one?
Yeah.
We need now the rules?
Yeah.
Okay. We got about 5 minutes, so try it, take another minute or so, and then we'll go through the name together.
What does the number tell you what it's connected to?
Right, the number tells you what which one it's connected to. You think you got it? What do you got? Let's see.
2-methyl 3-methyl pentane.
Okay. Anybody get something else?
I don't think it's right. Diethyl methyl pentane.
Like that? Okay. Anybody get something else?
2-ethyl 3-methyl pentane.
Okay. Anybody get something else? Nothing? All right. So what do you think? These are all pretty different names. I guess they're not that different. The first and third are pretty similar. What do you think? The third one?
Yeah.
Everybody likes the third one? All right. Well, that's good. They're actually all wrong.
But the closest one is.
But the third one is probably the least wrong. Still wrong, but the least wrong. You always see why these are wrong?
I know the second one is missing another number. But I don't know.
Second one's missing some numbers. And the first and third one only differ by the placement, the number. The third one is actually a decent description of the structure. The problem is it doesn't quite get the longest chain right. So the third one is talking about this as the main chain, right? 1, 2, 3, 4, 5. So that's 2 ethyl and then 3 methyl. But I can find a longer chain. Right. So let's say we start here instead. We could go 1, 2, 3, 4, 5, 6. So we can get a longer chain by picking this one as our main chain. So that's actually a hexane. And that makes the substituents here and here. So we would number 1, 2, 3, 4, 5, 6. And now our methyl groups are on 3 and 4. So that's going to be 3, 4, dimethylhexane.
Oh, I get it.
There's a methyl group connected to 3 and a methyl group connected to 4.
Right, and they're down because there's two.
There's di because there's 2 of them.
When you do that, is it just to show like the substituents versus the other one, or that's one word, right?
That's all one word, right? Just like it would be like when I typed it. I just did it in different colors to kind of show
Yeah,
the substituents versus the main.
Wait, where did you get the dye? Oh,
Because there's 2 of them.
and then.
If it were just 3,4-methylhexane without the di, that would make it sound like the same methyl group was connected to 2 different carbons at the same time.
What if
Should
it
be a little
was
different.
and the CH2?
Where?
Maybe first one.
Here? Couldn't have that because that carbon wouldn't have enough bonds. So that wouldn't come up. All right, so this will definitely take some practice. We'll do some more with this next week on Tuesday. Or actually, no, I guess not next week Tuesday because we'll have the exam. But Thursday after that we will. And we'll go on from there. That's right. Not going to be on this. We'll be on the nuclear stuff.
This is not gonna be on the test either, right?
This will not be on the test either.
And methyl and CH.
3.